Alright folks, welcome to week 3. I'll just do a quick overview on some of the things you guys need to do. Just like any other week, check the announcements. There's metric conversion problems that you guys are going to have to do. So this is a Google document. So in there you'll actually find problems that you need to complete. So you can, pen and pencil the work out, on your own on the side, but you'll actually want to type in the answers to those problems right in the Google document that you guys will copy for yourself, and you'll share that back with me. And then there's also a metric conversions quiz. You will also find a little bit of, or one question, I guess, at the end of the metric conversions problems that has to do with calculating percentage of error. And there's a video embedded in this assignment. In the Google Doc, there's a YouTube link. But on the bottom here, I also included that same video link. So if for some reason it doesn't work or you can't find it there, you can look at it here. But what I'm going to do for you right now is I'm going to show you a bunch of example problems using the tables that are inside of the metric conversion problems assignment, because you're probably going to want to see some examples on how to solve these prior to attempting them on your own. So when you guys open up the metric problems worksheet, you're going to have a couple of different tables. You're going to see one that looks kind of like a staircase. Looks like this, and you're going to get another one that's just a prefix table that has lists of the prefix, the symbol, multiplier, and then the exponential form. So I'm going to show you two different methods for doing metric conversions. The first method that I'm going to show you is going to work. This would work in theory for any any metric conversion you wanted to do. However, it gets to be a bit cumbersome when you're dealing with numbers that are larger than a kilo or maybe smaller than a milli. You got to start moving the decimal place a lot of, a great distance, and that's not exactly the most efficient thing to do when you're dealing with numbers that are way big or way small. So we'll look at this. I'll fill out the chart with you. This kind of shows you at least the workings on how the metric system works, or how metric conversions actually work. So what you guys will see here is what they would call a staircase. It has prefixes listed all the way from kilo down to milli. It shows what their values are, kilo being 1,000, hecto being 100, deca being 10. The base unit they don't have labeled, but the base unit is basically a multiplier of 1. And then deci, centi, milli is a tenth, a hundredth, or a thousandth of whatever unit you're talking about. Now the base unit is dependent on what we're actually measuring. So if we're measuring mass, then the base unit would be a gram. If we're measuring a volume, like how large something is, it would be the liter. And if you're measuring a distance, like how far something goes, we would use the meter. Now you could have any combination of these prefixes, a kilogram, a hectogram, a decagram, decigram, centi, and milligram, or a kiloliter, hectoliter, decaliter, and so forth. The prefix is basically a multiplier of whatever value you have. There's abbreviations that go with these, which you've seen in the other chart, but they don't show here. This is basically what you would use in order to identify, what prefix is actually being used. Kilo uses the K, hecto uses an H, deca actually uses DA, deci uses a lowercase d, centi uses a C, and then milli uses a lowercase m. So I'll try to help you guys identify which one is which as they're listed in the problems. Sometimes people get a little confused because sometimes they'll see a base unit by itself. For example, a meter and a milli have the same letter, but you don't ever have a milli unless you already have a meter or a base unit present. So if you ever see an M or a G or an L, any of those by themselves, it's always talking about the base unit. The only time you're converting to milli or from milli is when you have an M and another M, because there's actually a prefix there instead of just a base unit. Okay? So I'll go through some of these. We'll start up pretty easy, and I'll show you how to use the staircase. First practice problem is showing we're converting from 1 centimeter to 1 millimeter. So the trick is you look at where you start and where you're going to finish. So in this situation, I'm starting at centi and I'm going to milli. And using the staircase method, it's simply going to show you what direction to move the decimal place When we move the decimal place to the right, it's the same as multiplying by 10. And for every single step is the same as a multiplier by 10. So when you guys start at centi and you're going to milli, I'm going to multiply by 10 or move the decimal place to the right 1. I started with 1.0 in essence. It doesn't show 0.0, but the decimal place is after the 1. So if I move the decimal to the right 1 place, I basically need to add a 0, and that'll get me to where I need to be. Okay? The next one is going from kilo to the base unit. So we start with 15 kilometers, and we're going to go to the base unit of meters. So I start at kilo, and if I followed the stairs, I would go 1, 2, 3 units to the right, which is the same as multiplying by 1,000. The other way to look at this is if you started with 15 and had the decimal place here, you move it to the right 3, and you fill in the zeros. Either way, you end up with 15,000. When you're converting to base units, you can almost write out the number just based on what the prefix is, because when you go from kilo to base, the base has a multiplier of 1, and kilo means 1,000. So this literally is spelling out saying I have 15,000 meters. And again, since we're converting to meters, we don't have to worry about the numbers being shifted anywhere after that. So it works out well. The next one is milliliters to liters. So I'm starting out with the prefix of milli. And milli is down here on the staircase. And we're converting it back to liters. So we're going 1, 2, 3 to the left. Whenever you move to the left, it is the same as dividing. So we're going to move to the left, divide, 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 which is the same as dividing by 1,000. The decimal place for 400 would be at the end of the 2 zeros. You'd move it back 1, 2, and 3, which means that your decimal place now would be in front of the 4. So you'd be left with 0.4 liters. Then we go from milligrams to kilograms. Milli is at the very bottom of the staircase, right here, and kilo is all the way at the top. So as far as this data table, this is as far as you would actually move in any one direction. You would go 1, 2, 3, 4, 5, 6 to the left, which, remember again, to the left is dividing. So the decimal starts in front of the 5, so I would have to move it back 6 places. This means after the decimal place, I have 6 filler zeros, placeholders, for the kilo. Now remember, a milligram is very small, so you have a half a milligram, like think of like a grain of salt or something really small, and you're wondering what part of a kilogram, which is like 2.2 pounds, so something very large, what part of it do you have? Well, you have a very small part of it. It's even less than what you originally started with. Next one, we're going from the base unit to kilo. So if I scroll back up and take a look at where we're at, we start at the base unit and going to kilo, which is this direction. It's 3 directions to the left. So it's going to make this value smaller, 1, 2, 3. So by the time I jump back, I have 2 zeros, a 3 and a 7 and a 5. So remember, the decimal was originally between the 3 and the 7. If I move it back 1, 2, 3 spaces, I'm left with 0.03 or 0.00375. And then grams to milligrams. Again, we start at the base and we're going to go to milli. So we're going to go from the base to milli, which is 3 to the right, which is the same as multiplying by 1,000. So this one's going to end up to be 25,000 milligrams. Then we got 14 milliliters, and we're going to go back to liters. Milli is at the bottom of the staircase. And we're going back to the base. 1, 2, 3. Looks something like that. To move your decimal from milli back to the base, I started after the 4. I'm going to go back 1, 2, 3. So this gives me 0.014 liters. Next one, I'm going from meters to milli. So meter is a base unit and milli is to the right. So that's 10, 100, 1,000. I'm going to multiply 0.75 by 1,000, so 10, 100, and then 1,000 would mean the decimal would move to the right 3. And then we got kilo to milli. So if you're using the staircase, we start at kg, so the K is kilo, and the M is milli. So following our acronyms, here's kilo, here's milli. How many steps do we go on the staircase here? We got to go all 6. So there's 1, 2, 3, 4, 5, 6. Moving the decimal place to the right, 6 place values from there. So we had the 2007, plus we got to go to the right 6. So you're going to have the 2007 with 6 zeros after it. 1, 2, 3, 4, 5, 6. And put all the decimal places in. And then the very last one, we're going from liter to milli. Liter being a base unit and milli being to the right. 1, 2, 3 place values. So I'm going to go 13.5. If the decimal was here, we went 1, 2, 3 to the right. So you can put a comma in there, so 13,500. So that's how you do the staircase method. And again, this would work all the way up to larger prefixes or larger values. However, it gets to be a bit cumbersome because the staircase would get really big if we went all the way up, or went all the way down to say like nano, like 10 to the negative 9th, or we went all the way up to like tera or exo or something like that where the numbers get extremely large. So I'm going to show you a second method. So the second method is going to be using the exponents and subtracting the exponents or dividing out the values and then writing things in scientific notation, because again, some numbers get really, really big or really, really small, which means there's tons of zeros on the decimal or tons of trailing zeros, you know, before the decimal, would making the numbers really large. So I think that this way is actually even faster and there's less counting involved. In essence, you don't have to kind of move around so much. So here's the chart. I'll show you guys a few examples on this, and then of course you'll have your own problems to try on the worksheet. But the way this chart works is it shows the symbols, it shows the name of the prefix, and then it shows the multiplier over here. Now remember when I showed you the multipliers in the previous list, we only went up to kilo. So we either multiplied by 10, 100, or 1,000, or on the lower side of the staircase we only went down to deci, centi, milli. So we were keeping it in a pretty small range here, considering the size of numbers, which really is infinite. But we'll go down a lot smaller, go all the way down pico, femto, atto, all the way up to tera, peta, axa, or exa, sorry. And I'll kind of show you how this works. So the method that I found works good is you take a look at where you start and then look at where you're finishing. And I'm always going to list the value of the exponent of where we start and where we finish. So if I start here with 23.45 grams, and I'm trying to convert this to teragrams, I start out at gram, which is a base unit. And the reason I know it's a base unit, this isn't a Google or anything like that. There's giga and everything else on here. That's a capital G. This is lowercase g. If you just have one letter and it's by itself, it's always the base. The base unit has a multiplier of 1, which means that the exponent is 0. 10 to the 0 power is the same as 1, right? You're not moving the decimal when you're at the base. The base is just whatever you got. I have 23.45 grams, with gram being the base unit. I'm trying to convert that to teragrams. Well, teragrams, listed up here, you see the capital T, you follow it over, teragram is 10 to the 12th. Okay. Now the reason I'm listing these out is because what I'm going to do is I'm going to divide these exponents, or when you divide exponents, you actually end up subtracting. So if I have 10 to the 0 divided by 10 to the 12th, it's really 10 to the 0 minus 12. That's what I'm gonna end up doing with the actual exponents itself. If I have 0 minus 12, that leaves me with 10 to the negative 12. Now this is important because this is now my new multiplier for whatever original value that we had. So I'm going to rewrite this value like this, 23.45 times 10 to the negative 12th teragrams. This is the right answer. Like it's the right value. This is how many teragrams you got. If I took this decimal and I moved it to the left 12 places and filled in the zeros, meaning I would have a decimal with 10 zeros, because I go back 1, 2, and then an additional 10. I have a decimal place with 10 zeros, 2, 3, 4, 5 teragrams. That's how many I got if I started with 23.45 grams. Now, this answer is not completely wrong, but when we were writing numbers in scientific notation, there's a rule that says you should have the decimal place between the first and second significant figure. So when you actually go to write your final answer, it should be written as 2.3, and then I'm going to round this, 2.35 times 10 to the what value. Now, if I'm making this value smaller, meaning I'm dividing by 10, that means I need to make this number larger by a factor of 10. Because I'm not trying to change the value of this, I'm just trying to change how it's represented. That's all we're doing with any of this. We're not creating a new number, you're just representing it in a different way. 23.45 grams is the same as this, which is also going to be the same as 2.35 times 10 to the negative 11th teragrams. I got the negative 11 because I moved this to the left, which is the same as dividing by 10, which means I need to multiply this by 10. Add 1 to, this is a negative 12, so when I add 1 to negative 12, it's going to get me to negative 11. So this is the actual value that I would get for 23.45 grams. I would end up with 2.345 if you want to write it like that. I rounded it. The biggest thing I'm looking for is where is the decimal and what's the exponent value. Looks like that. So I'll do the rest of these also, if you guys want to continue to watch here. All right, the next one I'm going from gigagrams to kilograms. So I start out with 0.00456 gigagrams, and this is going to go to kilograms. So remember the first step, look at the chart, find giga and find kilo. Giga is 10 to the 9th, kilo is 10 to the 3rd. So I'll list them out. I have 10 to the 9th, and here I have 10 to the 3rd. Okay? So in essence, we need to divide the kilos by the giga to see what we're gonna end up with. So this is really 10 to the 9th minus 3. 9 minus 3 gives me 10 to the 6th. Bring this value straight down. 0.00456 times 10 to the 6th kilograms is what you're going to get. Again, not the wrong number, just written the wrong way. The decimal should be between the first and second significant figure. So it should be between the 4 and the 5. So I'm going to write this as 4.56 times 10 to the. Now I'm making this one larger by a factor of 10, 100, and now 1,000. Moving the decimal to the right 3 places, making it 3 larger. That means I need to take this value and make it 3 smaller. So I'm only at 10 to the 6th, so I got to subtract 3 from it, make it 10 to the 3rd. So there it is. 4.56 times 10 to the 3rd kilograms. Next one, we're going from milli to pico. So I'll write it out. We got 12,089 milligrams. And this is going to equal how many picograms? Milli is 10 to the negative 3. So we're already starting with the negative value. Pico is 10 to the negative 12th. So we're subtracting the second from the first. here's a prime example where you need to be careful. You'll get that double negative. You're going to have 10 to the negative 3 minus negative 12. So if you minus a negative, that turns into a positive. So this is really, in essence, like negative 3 plus 12, which is going to give me a positive 9. I bring down the value, the 12,089, and this is picograms. Now remember, the decimal right now is here at the end of the 9. We want it in between the 1 and the 2. So I need to move it back 1, 2, 3, 4 places to the left. So the value I'm going to end up with is 1.2, and I'm going to round this to 1.21. You could stretch it all the way out there if you would like, but I'll round it to 1.21, and then we're going to be at times 10 to the. So I'm making this smaller, 1, 2, 3, 4, or 10, 100, 1,000, 10,000. If I'm making this smaller by 10 to the 4th, I got to make this larger by 10 to the 4th. So if I'm already at 10 to the 9th, and I add 4 to that, that's going to give me 10 to the 13th. This is going to be 1.2, 1 times 10 to the 13th power. For number 4, we're going from micrometers. So here's 34 micrometers, and we're going to meters. So if we take a look, micro is 10 to the negative 6, meters is 10 to the 0, because it's a base unit. So obviously we don't have a whole lot to do with this one. You're going to have 34 times 10 to the negative 6 meters. The right value, just written the inappropriate way, is supposed to move this back one. So you're going to get 3.4. I make this one smaller. I got to make that one larger. One larger than negative 6 is negative 5. So you're going to get 3.4 times 10 to the negative 5. And then the very last one. We're going from a meter to a nanometer. So we've got 0.023 meters. I'm going to convert this to nanometers. So a meter is a base unit. Remember, there's only one letter. It's not a milli, it's just a meter. It would have to have 2 m's to be milli. So it's a base unit, so that's 10 to the 0. And then we're going to nanometers. There's the n. Nano is 10 to the negative 9th. Okay? We're going to subtract 10 to the 0 minus 9. Minus negative 9 gives you a positive 9. That is a double negative, right? So there's our times 10 to the 9th, our 0, 2, 3, and this is our nanometers. That would be, again, the right value. However, we want the decimal placed between the 2 and the 3. If I make this 10 and 100 times larger, because I'm multiplying or moving the decimal to the right, bigger, bigger, make this smaller, smaller. So you got to subtract 2 from this if I moved that 2 to the right, because I make this number bigger by 2 tens. I got to make this smaller by 2 tens. So that's going to be 10 to the 7th. So 2.3 times 10 to the 7th nanometers. All right. So there's your example problems for metric conversions. There's a lot of resources online for this also. So, and you'll see other methods for sure. I mean, there's a lot of ways to do it. Sometimes people like to set them up and show what you're canceling, all the units that you're canceling. I do like this one though, because you can do the same thing all the time. Just don't forget your double negatives and follow the process correctly. So you guys will have a few of those to do on the metric conversions worksheet. So think of this as your examples, and then the worksheet is your practice, and then there will be a quiz also, which you'll be graded on. All right. The video that I'm going to have you guys watch, and this is also same assignment, the metric conversions worksheet. There's a problem on there, or a video, and they want you to answer a question about an early philosopher named Eratosthenes, who was the first person to predict the circumference of the Earth. So this was approximately 2,000 years ago, and just by having some people walk across the desert, counting their paces and estimating the distance that it was between one city and another, they had vertical post in the ground on a summer solstice where if you're at 23.5 degrees north of the equator, nothing casts a shadow if it's a vertical object because the sun is directly overhead. But there was a city further north that did cast shadows at the same time in the same place. And he thought about this and said, well, that's strange. If the sun's rays are coming parallel to each other, and one city's got shadow and the other doesn't at the same time, then they must not be on a flat plane, they must be on a curved plane, which is in essence how he believed that the Earth was round, and then was trying to make a prediction based upon the distance they walked and the angle produced, assuming 360 degrees is a full circle. He knew what percentage of the Earth's circumference it was from the one city to the other. So he said, all right, well, if I can measure the distance, and then I know that 7 degrees out of 360 is that percentage of it, then I should be able to figure this out. So what I want you guys to do, in the video, it shows how he did it, and it shows the results that he got, and it shows the results that are accepted today as being the true circumference of the Earth. I want you just to calculate the percentage of error that he made by doing his prediction. So the way that you calculate percentages of error is you take the theoretical value, which is whatever is accepted to be true, like the real answer, minus the experimental. So whatever Eratosthenes got, you're going to subtract that from what we really accept the true circumference to be, and then you divide that by the true value. So I'll give you an example. Let's assume that I've been to the doctor's office and they put me on a scale, and my weight is, well, instead of doing weight, let's keep it science-like. Let's say we're doing my mass. Let's say they know 100% that my mass is 80 kilograms. Like, they know for a fact that my mass is 80 kilograms. That's the theoretical value, and that is the right value. If somebody did an experiment and they put me on a scale or put me in an inertial balance or did something crazy to try to figure out my mass, and they came up with 80, that means they're 100% right. They had nothing wrong. They would put 80 kilograms here, and they would say, all right, 80 minus 80, well, that's going to give you 0. Divided by 80 is still going to be 0. Like, they were not wrong at all. They were 100% right. Now, if they were off by a little bit, say, for example, that they guessed my weight to be 78 kilograms, well, you can see between here and here, 78 kilograms means that they were off by 2. So they weren't off by much, but they were off by a little. They were off by 2. If they wanted to find the percentage of error, you would do 80 minus 78, which would give me 2. 2 divided by 80 is the same as 2 80ths, which is the same as 1 40th, which is the same as like a fourth with the decimal place moved over. So a fourth is 0.25, so this is 0.025. As a decimal when you're done. This is the decimal representation of the percentage, so you multiply whatever that is by 100. So I'd bump that over 2, which would give me 2.5%. Okay? You guys are going to do the same thing with the data that you get in the Eratosthenes video. So they're going to give you an accepted value for the Earth's circumference, which is going to be more like theoretical. So that may be, I'll just make up a value. You'll have to watch the video to see. But let's just say the accepted value of the Earth's circumference is, 50,500 kilometers. The theoretical value then is 50,500 kilometers. That's the real value. If Eratosthenes predicted that the Earth's circumference was 50,000 kilometers, if this was the case, if you do that minus that, you know that he was off by 500. Like 500 was his amount that he was off out of how much. That's the part, this is the whole. The part was 500, the whole was 50,500. What percentage is that? You divide the part by the whole. Gives you the decimal representation, If you multiply it by 100, then that will give you the percentage of error. So try to use that. That's an example. Again, if you guys seek out other resources for this, that's perfectly fine. But that's what I got for you guys today. So if you have questions, send me an email. You can feel free if you need me to do more explanation. I can try to find you other sites. There probably will be more links or ideas, or maybe I'll throw a couple of other videos on doing metric conversions using some different methods too. If you, I mean, some of you maybe have been taught different ways, which is perfectly fine also. So with that though, have a good week, and we'll talk to you guys soon. Thank you.